Hello my dear students, welcome to Dramatic Science. My name Ayan. As we are going through heat transmission, today is lecture number 2. In the lecture 1, we have discussed about the classification of heat transmission and basically the process conduction. Okay, today's topic will be number 1, thermal resistivity, then Ingenhausz experiment, thermal diffusivity, the definition and the unit and the dimension, and then conduction through composite bar, that is series and parallel combination of rectangular bar. Okay, so let's go to the topic number 1, that is thermal resistivity. So okay, first topic is thermal resistivity, right? Here is a two comparison, one between heat flow and another between current flow. So at the case of heat flow, what we got, this is a slab and Q is the amount of heat entering this side, exiting this side. Theta 1 is simply the temperature of the two surface, A is the cross-sectional area, D is the distance. We got this formula. If you want to know how this formula came, please go through the lecture number 1 video. I will definitely give it in the description box. Kindly check it out. So keeping theta 1, theta 2 on this side, we can multiply D over here. KAT will come to the down, this one. At the case of current flow, according to Ohm's law, the relation between voltage and current, what we got? This one is the resistance, this one is the voltage V1 on this side and V2 on that side. So the difference V1 is greater than V2, definitely voltage difference is V1 minus V2, that is this one. I is the current flow and R is the resistance. So according to Ohm's, this is the law. So V1 minus V2 equals to I means current, charge by time, that is Q by T, and R is the resistance. If we compare these two equations, then these two equations are almost similar. So by comparing, we can say V1 minus V2 is similar to this difference. Q by T, that is charge by time, Q means charge by time will be equivalent to heat by time, and this R, resistance, will be equal to this term D by Ka. So this D by Ka term is called thermal resistance. Okay, this is the electrical resistance, and this will be the thermal resistance. So what we can write? Thermal resistance, comparing 1 and 2 thermal resistance are say T equals to this term D by Ka. Okay, as far we know, this electrical resistance can be written as, we can say R equals to rho L by A. No, I think you know the term. Rho is definitely the electrical resistivity. L is the length of the conductor and A is the cross-sectional area. If we compare these two, this thermal resistance and electrical resistance, then see, L is the length, D is also a length, D, A is the area, then definitely rho can be compared as 1 by K. So 1 by K can be compared as rho. This terminology is called thermal resistivity. So what will be the definition of thermal resistivity? Thermal resistivity is nothing but the reciprocal of thermal conductivity. That means the units and dimensions of thermal resistivity will be 1 by the units and dimensions of thermal conductivity. Okay, so that is thermal resistivity. Next we will go on Ingenhausz experiment. So now Ingenhausz experiment. So we have taken a vessel containing, suppose, water, boiling water. Okay, 4 rods of equal length and equal cross-sectional area but of different materials are attached to this vessel, like this one. This one is lead, iron, aluminium and copper. and this one is the wax on those 4 rods. If no heat is given to the boiling water, if boiling water boils, then the amount of heat will be transferred to this 4 bars, and the wax will melt. And after and steady state is reached. By the way, what is steady state? State is something in the metal or in the material where no absorption of heat will be taken place. So at the steady state, the length of this wax on those 4 metals came to a certain point. According to Ingenhausz, he observed that the length on lead is L1 and its conductivity is K1. That of iron is L2K2, aluminium L3K3, copper L4K4. And what he observed? He observed that this conductivity is related by somehow with this length of the wax. And what was the result? He observed conductivity, that is K proportional to length of the wax, K proportional to L square. This is his experiment, the result of his experiment basically, which says that conductivity of different materials are different. Thus, we can say, thus K1 by L1 square equal to K2 by L2 square equal to K3 by L3 square and so on is constant. So this is the result of Ingenhausz experiment, right? So that's simply a basic experiment. Next we will go on thermal diffusivity. Thermal diffusivity, that is as symbol small h, can be defined as the ratio of thermal conductivity and thermal heat capacity in unit volume. The symbol of thermal conductivity is K, that is fine, but the symbol of heat capacity in unit volume is rho s. How? See, heat capacity is simply mass into specific heat, that is m into s. And if we consider unit volume, then simply mass is density, that is m equals to rho. That's why heat capacity in unit volume is rho into s. So H equals to K by rho s. Now we need to find the unit and dimension of this H. Kindly pause the video, do the calculation by yourself, and next I will do it here. Pause it. Now the units. First one will be the unit of thermal conductivity, that is joule meter inverse, Kelvin inverse, second inverse. Then is the rho, that is density, kg per meter cube. S, specific heat, joule per kg per Kelvin. Joule gets cancel out, Kelvin inverse cancel out, kg minus 1, meter cube meter minus 1, so this will be meter square and second. Similarly in CGS, centimeter square second inverse. And similarly we can also find the dimension using units, that is L square T minus 1. So that is thermal diffusivity. One thing to know, thermal diffusivity is also called thermometric conductivity. H is also called thermometric conductivity. Okay. So this one is the part of thermal diffusivity. Then now we will go on conduction through composite bar. First of all, we will start from a series combination of 2 bars. So series combination of 2 bars. These are 2 bars, conductivity K1, K2, length L1, L2, entering temperature theta 1, theta is the intermediate temperature, theta 2 is the exiting temperature, Q is the heat. So if we combine these 2 bar, we will get the equivalent bar, this one. Conductivity K, length is L1 plus L2, the whole length, theta 1 temperature difference, theta 2, Q is the heat. So for these 2 bars, we can write this equation, K1 into cross-sectional area of 2 bars will be same, A, theta 1 minus theta into time by the distance, that is L. Similarly for this, then K1 AT gets divided in down this one. We are adding no numerator and denominator. So if we add this minus theta and plus theta will get cancel out. So here we will have theta 1 minus theta 2 equal to this term plus this term. This is equation number 1. Now if we consider the composite bar, that is the equivalent bar. So for this, Q is Ka theta 1 minus theta 2 into time will be same, that is T, by L. L is simply L1 plus L2. Here also KAT gets divided, so this one. See, these two terms, this equation 1 and 2 are same, so we can compare them. We can compare them and can say from 1 and 2. From 1 and 2, what we can say? See, Q are same, theta 1 minus theta 2, theta 1 minus theta 2 are same. Then this lower part will be equals to this lower part, that is L1 by K1 AT plus L2 by K2 AT will be equals to L by KAT. We need to find K, so simply AT gets cancelled out. Thus L1 by K1 plus L2 by K2 will be L1 plus L2 by K. Simply L is L1 plus L2. That means K can be written as K L1 plus L2 by L1 K1 plus L2 K2. So this is the formula. I hope you can see it. This is the formula, L1 plus L2 by L1 K1 plus L2 K2. This is the equivalent conductivity. So now, okay, parallel slab. So parallel combination of two bars. These two are parallel bars having cross-sectional area, different cross-sectional area, that is A1, A2. Conductivity is different. Here length will be same. At the series combination, length was different, cross-sectional area was same. Here the reverse will happen. So theta 1, theta 2 temperature difference, and definitely theta 1 will be greater than theta 2. Heat entering and heat exiting is Q1, and for this slab is Q2. At the case of equivalent bar, theta 1, theta 2, conductivity K, its area will be the total of area of these two slabs. So Q is the heat. So Q1 can be written as, for this slab, K1 A1 temperature difference into time by length L, and simply for this one Q2 will be this one. For this equivalent slab, we can write this formula, Ka temperature difference time by length. Here we will consider that the amount of heat of these two surfaces, basically the total amount of heat, that is Q1 plus Q2, will be equals to Q. That's why we have written this, Q equals to Q1 plus Q2. Then the values has been written, and see, T, theta 1, theta 2 and L are same for both for those three cases. So we can cancel them. We can cancel them and we can write this formula, Ka, K1 A1, K2 A2. We need to find K. So K will be divided by A. And what is A? A is the total area of this equivalent bar. So this is the equivalent thermal conductivity of this composite slab. Okay. So guys, that's for now. These 4 topics, basically lecture number 2 is completed. In the lecture number 3, we will learn about the process radiation and the few laws related to radiation. So I hope you have learned something new, and if it was helpful, then please give a thumbs up, do comments, do give any kind of suggestion, and please do subscribe my channel. I need your basic help to grow. That's all for now. Thank you. Have a great time. Have a great life. Thank you so much.